parallelogram below to write each vector in terms of vector x and vector y. So instead of using AB and BD and AC like they are currently written on the blanks, we're going to fill in the blank next to it using only vectors x and y. Well, in a parallelogram, we should know certain properties. What do we know about opposite sides of a parallelogram? They're parallel, and they are also congruent. Yeah. So if this side is vector x, then this side should also be vector x, right? They're the same as far as measurement goes, right? Okay? And if this side is a length of vector y, then this side over here should also be a length of vector y, right? Okay? All right, so we know that opposite sides are both parallel and congruent. Do we know anything about the diagonals? What do those diagonals do to each other? They what?
Complementary.
Not complementary, that would be their angles.
Yeah.
So they're not going to be the same size because clearly from A to C is a lot further than it is from B to D, right? But those diagonals should do something to each other. What does it do? What do the diagonals do to each other? What do we know about the diagonals?
They cross.
They cross and do what? That's what cross means, yeah, intersect. What?
Perpendicular.
They could be, but they're not always, right? Because it looks like here, these angles would probably be smaller than these ones here, right?
Yeah.
So what do those lines do to each other where they're intersecting? What did this line do to this one where they intersected? Look at it.
Is that what they're equals?
Yeah, it splits it in half. This piece and this piece are the same size. And this piece and this piece are the same size, right? Diagonals bisect each other in parallelograms. Did Anna remember that?
No.
Oh, okay. I could tell one of y'all knew because y'all were looking at each other. All right, so now that we have gathered this information, that should help us with filling in the blanks because we know what pieces are the same size and which pieces are not the same size. And we're comparing them all to the vector x, which is the top and bottom, and vector y, which is the left and right sides. All right, so first, they start out easy on us. They say AB plus BD. Okay, well, AB would be this side here, right? And BD would be this side here. Okay? So what do you guys think? What could that maybe be congruent to? What would that make me end up with the shortest distance? Remember, this is where I started, right? And where did I end up at? What letter? D. So what's the shortest distance from where I started to where I ended? Okay, which is vector x. Remember, that's what we do on those ones where we draw them, right? We draw the 2 or 3 or 4 vectors, however many it asks, and when we trace the shortest distance from where we started to where we ended, right? Okay? Then for AC, we start at A, we end at C. What do you guys think? How would I get from A to C? So remember, it has to be in terms of x and y. So what vector would get me, or what vectors, plural, would get me from A to C? How would I have to travel to get there? Yeah, I'd have to go along both of them, right? So I can write that as vector x plus vector y, or y plus x. Order doesn't necessarily matter when we're adding. All right. Then it asks us to find vector dA. Okay, well that would be from point D back this direction, right? Okay. So remember our vector x was traveling this way, right? How do we make it go in the opposite direction? A negative, yeah. So I just put a negative in front of that vector x. Good. Okay. What about vector CD?
Negative y.
Good. Okay. Now they ask about vector AE. Okay, so A would start at A and E would end at E. Okay, so I'm not going to travel any full vector length, right? It looks like, though, I could go maybe like part of the way here and then part of the way in. So how much of each vector would that be?
X plus y divided by 2.
Right, half of them, right? Half of vector y and half of vector x. So he said you can add them and divide by 2, or you're also welcome to write it as 1/2 y plus 1/2 x, whichever way you prefer to think of it. Okay? Then they ask about vector dB. Okay, so that would be going the opposite direction. So what would I put there?
Is the same with negative?
Right, it would be kind of like AC, right? But we're going to be subtracting because we're going to go the opposite way. So we're going to say vector y minus vector x. Okay. What about DE? That would start at D and end at E.
Something's AE.
Similar to AE. I'm just going backwards, right? I'm going up the vector. So instead of addition in the middle, I'm going to have subtraction. Good. So I'll have 1/2 vector y minus 1/2 vector x. Okay. Then they ask about vector BC, so that'd be traveling this way, plus CD, which would be traveling this way. So BC is going in the correct order, right? So that one's positive, and that would be vector what? X. Okay, but CD is going the opposite direction from the arrow, right? So that one I would have to put minus, subtraction. Very good. All right. And then we've got BC plus CA. So BC plus CA, which would be going this direction. Okay, so I started at B, and I'm going to end up at A, right? So what's the shortest distance from B to A? Vector y, but I'd be going down that side, right? So it would be negative, right? Okay, so that was just testing us on knowing our directions, really, okay? All right, so let's move on to some new information. So it says, if you have force or velocity that is in a direction theta, measured from the positive x-axis, then the vector components that for that force or velocity would be written as the vector with velocity times cosine of theta, comma, velocity times sine of theta, or force times cosine theta, force times sine theta. So depending on if they tell you velocity or force, we will multiply it times both our x and y component, which for us are going to be cosine and sine. All right, so example number 2 here says if a box is being pulled with a force of 20 newtons at an angle of 37 degrees from the horizontal, What is the horizontal and vertical component of the force? And which one is greater? All right, so this time they said that we were given force, right? So I'm going to write it like this. So I'll have force, which they said was 20, right? Times cosine of theta. And what did they tell us that theta was? That should say angle there. 37, yeah. All right, comma, again, force, which is still 20, this time times sine of theta. All right, so if they wanted it exact, this is how we would give it. But in order for us to tell which one's greater, we need to actually have some numbers, right? So, making sure my calculator's in what mode? Degree, right? Because both of these were given in degree. You're going to type 20 times cosine of 37 into your calculator and tell me what you get there. All right. So 15.97. All right. What about when you type in 20 sine of 37? Good. All right. And they asked which force was greater, the horizontal or the vertical? Horizontal, right? Because this is going to represent our horizontal. So we'll say horizontal force is greater. Good. Okay. Example number 3. This one says a boat travels 15 degrees east of north for 35 miles and then turns to travel 27 degrees south of east for 50 miles. Okay, so let's label that on our picture over here. So let's pretend this is kind of like a compass. All right, so we're going to go 15 degrees east of north. So this is my north. I'm going to go 15 degrees over. All right. And it says we're going to travel that way for 35 miles. So here I travel 35 miles. And then once I get to that spot, it says that we then turn and travel 27 degrees south of east. Okay, so I'm going to basically put another little compass right here. From the spot where I turned. And it says we're going to go 27 degrees south of east. So 27 degrees south would be to go this direction from east. That'll be 27 degrees. And they're going to travel that way for another 50 miles. All right, it says to write the vector in component form that represents the path of the boat. So I'm going to write this just like they gave us for our formula on the front page in that little box there. All right, so for our first vector, we went 35 miles. So that's what I'll put in front. 35 miles times cosine of theta. Now this part is where it gets a little bit tricky because your degree or your angle should always be measured from the x-axis, right? So in this case, for that first vector, this would be my x-axis, right? So I know that it was 15 degrees from the north part of my compass to that line I drew. So how many degrees would it be from the x-axis to that vector? 75. All right. So this would be 75 degrees, okay? Because we always measure from the x-axis, okay? And we know that, guys, because we know that this is a 90-degree angle, right? We just subtracted 90 minus 15 to give us that 75. Okay? So you might want to make note of that. Always measure theta from x-axis. And not only the x-axis, right, but 0 over here, right? Just like on our unit circle. We always start over on that right side of the x-axis. Okay. All right, so there's our x component. Remember, the y component should pretty much be the same thing, just with sine, right? So it'll be 35 sine of 75. Okay? All right, and then I need to do the same for the second vector, right? Because I'm going to put them together to see where I ended up. This time we traveled 50 miles, so it'll be 50 cosine of, I'm going to look up here. For that 27 degrees, I kind of went backwards from the x-axis, right? So if I'm going to measure what or how many degrees that actually is, I'm going to start on my x-axis and travel in the positive direction to get to that vector. Well, I know if I made it all the way back around, that's 360 degrees, right? But I stop 27 degrees short of that. So how many degrees? Right. So 333 degrees would be our angle. And then same for your y component, but with sine. All right, and then if I'm looking for where I ended up, right, our end spot, I started right here. I ended up at the end of this vector over here. So the shortest distance, what am I going to want to do with those two vectors to find that spot? Add them. Yeah, I'm going to add those two vectors together. So this is where you'd want your calculator. You'd add your 35 cosine of 75 plus 50 cosine of 333. Just adding the two x components together. What did we get there? Good. Okay. Now I need to do the exact same for my y components, right? So now I'm going to add together 35 sine of 75 and 50 sine of 333. And what do we get for our y component? All right. So that would be our vector in component form. Okay, so there's the vector that represents the path that we traveled, right? Then part B of the same question says how far did the boat end up from where it started? So now we're talking distance, right? Or magnitude. And do you guys remember from last lesson what we do to find magnitude? Right, we're going to square those two pieces from our vector, right, and put them underneath the square root and add them together. So that's going to be the square root of 53.609 squared plus 11.11 squared. Which, of course, this is going to be an approximation because these numbers, 53.609 and 11.11, those have already been rounded once, right? So if I'm using them again, it's definitely an approximation. So I'll say about, what do we end up with when we square those, add them, and take their square root? Good. Okay. All right, we got one example left. It says if James, Jack, Jared, and Jake play a tug of war game where each pulls with a given force and direction that's shown on the graph, who wins the game? So, I'm going to need to do exactly what we did on part A here, but this time instead of having 2 vectors, we have how many? 4. So same thing, but do it for all 4 people. And then we are going to need to know where we end up. So what do I do to figure out where I end up? Add them all up. Yeah, add them all up. And then you should be able to determine who wins based on where you end up, right? Whoever's quadrant I end up in should be the answer. So I'm going to let you guys try example 4, since it's so similar to part A from example 3. And then we'll share what we come up with.
To x.
This would be theta.
Yes, but it's in accordance to the x-axis, the positive x-axis, so you would go the entire way. So it'd be 150. So that's your kids do math. And then it'd be 3 sine of 150. Yeah. It'd be 150.
Degrees. Yeah, that's what that's what I did. I just didn't know where I would see what you're saying, sorry. It goes this way anyways.
It goes this way normally. Start from here, you get to 90 degrees, here, 180, here, 270, here, 260. Why does this guy get to go this way? They're still going the same direction. Yeah. They still go here, that guy's still going here, this guy's still going here.
This is 20 degrees from 90.
If we go this way, it's like, oh, go this way, it'd be going against, would be negative. Okay, that's
80 for James?
Yeah, for the degree.
Oh, yeah, it's 70.
You get 150. I might have done something wrong as well. I probably got a negative. Yeah.
Yeah, I got a negative.
Oh, wait.
And it's still Jack. Yeah.
I was going to.
Oh,
I was thinking of the other example.
I wanna live.
Force is greater, so I thought.
I haven't done it yet, I'm not finished.
All right, so let's talk about the vectors that we came up with for each person. So for James, they said James had a force of what? Of 50, right? And what was the degree for James? 70, right? Because just like we said on the previous example, we go from our positive x-axis, right? So I'd be measuring from here to here. So my vector for James would be written as 50 cosine of 70 degrees, comma 50 sine of 70 degrees, right? Okay. What about for Jack? What was Jack's force? 48. What was Jack's angle?
$150.
150. All right. And then what was Jared's force?
46.
46.
30.
What was his angle? 230. Very good. And then finally for Jake, Jake's force was 47. And what was his angle? Good. All right, and then to determine who wins, we need to determine where we're going to end up, right? So just like last time, to determine the vector of the path traveled, I'm going to take all of these vectors and I'm just going to add them all up. So I would add all of my x components and I would add all of my y components. So when we added our x components, what did we get there? Very good. And what about for our y's? Very good. All right, so remember, this is my x component over here, and this is my y component. So if I have a negative x value, that tells me I'm in quadrants 2 or 3, right? And then my y value is positive, so I must be in which quadrant? Quadrant 2. So who won? Jack. So Jack wins. All right.